Hey guys, it has been a while, and mostly it's because I've been like on vacation for a while, and then just kind of not feeling like doing anything. So that's why I haven't seen a video in a while. But now we're back. Now we have a div 2 in front of us. So let's just do that. So you have an array of integers. I hope the audio is fine. I redid the setup because I had to take everything. I also have a new computer, so you'll be seeing that soon, I guess. But not right now. I'll have to put more effort into making that work. Anyway, you have an array, you want to split it into two non-empty subsequences. So like split the array up such that each element ends up in one of them, and the average is as high as possible. Okay. How do we do that? Do we put the biggest one by itself? What happens if we do? Well, the samples seem to support that. So if we put the biggest one by itself, then like the intuition is that the average is the sum divided by the length. Whoa, wait. The average is the sum divided by the length. So if we put the bigger one like with some other ones, then it will be divided, so its contribution will be less. I don't know if that like is it, but well, let's see. We want everything smaller to be divided as much as possible. Actually, I don't know if that makes a difference. Okay, how does it work? When do we not want to do that? Oh yeah, I think that's right, because say we have like something like 1, 2, and then 3. So we have the biggest one by itself. Then if we move any other element over to this, then the average of this will decrease because it loses the largest element. And the average of this will decrease because it gets a smaller element. So it doesn't help. So if you start off with the biggest element in its own thing, and then everything else in the other one, then it doesn't help to move an element over. So I think that should be good. Now we are going to not FST because of precision issues again, but this time it's just a single division, so it should be fine. So we're going to take the sum of the first n-1 elements. Those are going to be in the first group. Ants plus equals AI. Actually, first we have to sort so that the smallest elements are at the beginning. We divide by n-1, which is okay because n is at least 2, and then plus equals AI. Hang on, I'll fix that. It should be n-1, the last element. I makes no sense, of course. Also, I'm still using this like folder from camp. I just haven't like modified it at all. Seems good. I also have set precision by default. You're gonna need that if you want to print it. Otherwise, it'll do like 1e plus 6 or something. I might show that later. You want to use set precision and probably the fixed form. It's sort of like a magic line that makes printing doubles work. By the way, I'm not actually trying that much for speed this time. I'm just going for it. You have an array of n distinct integers. You want to sort that array in non-decreasing order by doing the following operations exactly once. So split the array into exactly k non-empty subarrays, such that each element belongs to exactly 1. Okay, so same thing as the previous thing. Split it into k groups. Each element must be like in one group. Yeah. Reorder them arbitrarily, and then merge. So okay, so for every say we have this like 1, 3, 2, or say we have like 1, 4, 2, 3, 5. Essentially, for every pair of elements where, actually no, that's not true. Never mind. Well, it's kind of right. Essentially, we have for every pair of elements where this element, can we like, why do they have to be like that? For every element where this element is right after this one, or like, sorry, for every pair of adjacent elements where like this is fourth in the sorted array, and this is first in the sorted array, and this is second, or yeah. So these are next to each other, but they shouldn't be next to each other because we need 2 and 3 in between. So it means we have to do a split here. And similarly for this, these are right next to each other, but they can't be because, well, for one, there has to be stuff in between, and also this has to be after this one. So we have to do a split here. Here, these two are next to each other, and they should be next to each other because they're next to each other in the sorted array. So we do not need a split here. So this is good, and we also need a split here. So basically, we're going to count the number of splits we need to make. And then we'll see if we have enough. Like if it's less than or equal to k, then it's valid. Otherwise, we need to make all these splits, so it's not going to be possible to do this. So now what we need is the position in the sorted array of each element. And I guess, okay. So we're going to create a list of pairs. It's going to sort first by value and then by index. So it'll sort of, or first by value, and then it'll like have the indices with them. So now like this array P will tell us exactly what the sorted array is. And then we can do something like B being the location in the sorted array of the index corresponding to the ith element in the sorted array has that position. That sort of makes sense. And then ants plus equals bi is not equal to. It's basically saying if it's not valid, if this is not directly after, then we need to make a split. Then we just check the number of splits we need to make. Any case, so I can do capital. Does the exact opposite. What? What is it doing? Okay, right. Never actually read in K, so that makes sense. Perfect. I think it helps to think. If you don't understand what I'm doing with this, it helps to think about it a bit more. Like P is the sorted array, and then we're using the indices so that we know what the original indices were, and then we can get information from that. Anyway, now we have a game, and I love game theory so much. So let's do this. Okay, it's like kind of a game, but not really. I guess it's not a game theory. Maybe. So the bitwise AND has to be greater than the XOR. Okay, so first things first, when we're thinking about bitwise problems, specifically with bitwise operations, it may help to consider each bit sort of separately, because bitwise operations handle each bit separately. Like the 0 bits sort of get treated together, but they don't care about the 1 bits, and the 1 bits don't care about the 2 bits, and like etc. So imagine like the simple case where like k equals 1. So we have a single bit to work with. So for example, like 0, 0, 0, 0, or sorry, like each element can either be 0 or 1. So let's take like n equals 3 as an example. So suppose we create an array like this. Wrong answer. That's fun. Sequence? No, yeah. Exactly k doesn't matter. What did I mess up here? Okay, so reading the input. We're going to sort by that. bi plus 1 is not equal to bi plus 1. So that is not the case. We need something in between. Oh wait, it's an off by 1. Yeah, the number of splits we can actually make is k minus 1. That is my bad. The number of subarrays is k, but that means that we can only do k minus 1 splits. So this has to be k minus 1. That is a good thing to note. Surprised that passed samples. Yeah, okay, so back to this. Think about like an array like this. Well, actually, let's think about bitwise AND in general. Bitwise AND, if you look at the Wikipedia page to like look it up, basically it's going to be, so like the AND is equal to 1 only if all of the rest are 1. So yeah, so all the rest are 1. And basically what that means is, what does it mean? Let's see if we got this actually. Okay, Q is a bit long, but I guess it's fine. So if we even if we have like a single 0 in the array, so we have like 1 1 1 1 1 0 1 1 1 1, it's still going to be 0 because there's this single 0 in here. So we want the bitwise AND to be greater than or equal to the bitwise XOR. So what if the AND is equal to 1? Then we have all 1s. So no matter what, this the bit in this position is going to be greater than or equal to the bit in the other position. Okay, there is some parity off. So there's some parity stuff here. That's cool. Love that. So the bitwise AND, so if everything is 1, then the bitwise AND is 1. So is this greater than or equal to the XOR, or is it greater than the XOR? Well, the XOR is essentially the sum of everything modulo 2. So in this case, it would be there are 5 1s, and then that mod 2 is equal to 1. Or in particular, it's 1 if there are an odd number of 1s, and 0 if there are an even number of 1s. So in this case, the XOR would be 1. But what if we have something like 4 1s? Then the AND is equal to, that was a horrible ampersand. Then the AND is equal to 1, but the XOR is equal to 0. So in this case, it's actually greater. And so this is where the number of digits sort of comes into play. And it's because if it's greater, K is like, oh, K is large. That's fun. So if it's greater, then essentially, it means that like everything else can sort of be whatever it wants. And that's because of how digits work. Like, if one digit is greater than the next, then all other digits don't matter. No matter what, the first number will always be greater than the second. Because like, say we have like 1 0 0, and we're comparing it with 0 1 1, then this is like 4 and this is 3. And this digit is more important. So basically, if we have a single point where it's greater, then where this bit is greater, then all the other bits don't matter. So in the case of, now it sort of comes down to parity, because if n is even, then if we have all 1s, the XOR will be 0. And therefore we do have this greater thing going on. So it kind of, we have to like do some special casing. But if n is odd, and theoretically you can avoid it with like a digit DP, but I don't want to do that. There are easier, simpler ways to do this, so I'm not going to overkill that. But it'll sort of end up in the same way, actually. Alright, so if n is odd, then no matter what, the AND is less than or equal to the XOR. Because the only time the AND can be greater is when it's 1, but when the AND is 1, the XOR is also 1 when n is odd. So really, like, how many 1s can we have in the array? How many 1s can we have in the array for this bit? Well, we can have 0, because then the XOR would be 0. Or we could have 2, or we could have 4, or etc. up to n minus 1. Note that this is even because n is odd. And then we can also have n, because then the bitwise AND is that. And these are the only possibilities, because no bit can be less, because otherwise the whole number will be less. So for odd, it's just this. It's the sum of n choose all of this. So it's the sum of n choose 0 plus n choose 2, and etc. Because it's the number of ways to have this many zeros in the array. And then we take that to the power of k, because each bit is independent. So for n being even, it's a bit more annoying, because there could be a point, again, where one digit in the AND is greater than the XOR, in which case all subsequent digits don't matter. So the case where that doesn't happen is the number of 1s is equal to 0 or 2 up to n minus 2. And if we have n, then the AND is greater than the XOR. By the way, I'm sort of working this out for myself too. So what we're going to do is we're going to fix the first point where the AND is greater than the XOR. The first point. So in this case, the AND must be less than or equal to the XOR, and in this case, anything. Because here, this is already greater, so the comparisons of the rest of them don't matter. So for this, we have all of these possibilities, because this is where it's greater than or equal to, or specifically it's equal to, not less than or equal to. This is sort of the structure of the number we're working with. So we have all these possibilities. If we're at position I, then this is to the power of I minus 1. And then this is everything to the power of, it's just 2 to the n. So odd and even are kind of separate. Jesus. My mic just fell over. Alright, I'm going to see if that messed with something. Hope the audio is still good. Did get messed up last time. I'm going to move this wire back here so that doesn't happen again. Okay, I hope that's good. I really don't know what happened before. Somehow it just got totally messed up, but I hope the mic is picking it up fine. God, why is audio so stressful? So, once again, we're reading in a number n, a number k. I'm going to pull out my number theory template. No, mod operations, which is sort of combinatorics at the same time, because we need n choose k. So, gen factorial 3e5. It only has to be up to n, which is 2e5, but I don't care. It doesn't matter. Just big number. Ow! What? I don't know what's up. Okay, so if n is odd, then for l equals 0, I is less than n, I plus equals 2, ants is equal to ants plus there's one possibility for n choose n, which is like all ones, and then the rest is the sum of this. And then k mod. Okay, so this is the easy part. Just gonna make sure it works on the samples. Pretty sure it will. Like, who knows? The samples are slightly garbage, so yeah, gets 5. Now we have the hard part, which the samples don't cover at all. Thank you for that. And the way this is going to work is, once again, we're going to fix this position. So first, we're going to count the number of ways to have the AND equal to the XOR. So code is actually surprisingly similar. So this is EQ. So now we're going to fix the position where it happens. Plus. So we have I minus 1 positions if I is greater than 0. Cur times equals the number of ways to have the AND equal to the XOR to the power of I minus 1, which is to say power of EQ I minus 1 mod. And also, if I is less than n minus 1, we also have 2 to the this. Yeah. In fact, I'm gonna make this equal because there is a possibility that there's never this point, and so the end is always equal to the XOR, and that's sort of the odd case actually. Yeah, which is interesting. It's actually the exact same code. So, oh, this should be up to k, not n. So if I is less than k minus 1, cur. So what is the answer here? It's 2 to the what? Each level here is 2 to the n. And the number of levels we have is, I'm guessing, n minus I minus 1. We have like 0, 1, 2, n equals 3. The I is here. Then we need 3 minus 1 minus 1. That's the number we have here. So yeah, n minus I minus 1. If you're confused by indexing, it usually helps to work out like a small case for that. Okay. Now we roll. Should I trust the sample? I don't know. Well, this is useless. This is also useless. Everything here is useless. Especially just figure it out for yourself. I guess we can just work out a small sample. So let's see, what do we think about this? Well, there are 16 possibilities, which sucks. Ah, whatever, it's a div 2. I'm gonna submit, have faith. If m mod 2 is equal to 1, yeah, I think odd is right. Then we do the same thing to find the number of equal, and then we iterate over the position, we like do the math that I did, and then everything should be maybe fine. Actually, this is kind of confusing. How is I minus 1? This should be k. That's a start. Wait, this actually, I don't actually understand. It doesn't make a difference here, but I should change the answer for this? No. Wait. The confusing part is that this plus 1 doesn't add up to n. And that's because I'm 0 indexing. So this should actually be 0. This should be I, yes. A little sanity check there. This should be I because we're 0 indexing. So yeah, that's a thing. We have, if I equals 1, we have this many positions that work. That's why I look at my code all the time, because often there are mistakes like this. So I don't need this. Actually, it doesn't matter. If I equals 0, then this is to the power of 0, which is fine. And yeah. This is int plus cur. Is mod the right thing? 10 to the 9th plus 7. Yeah. I'm gonna blind submit and just see. Or not blind, I guess. I mean, I looked over it, but we'll see. Awesome. Okay, so we're gonna actually create our own samples because these are literal like garbage. Like you can throw these in the garbage and you couldn't tell the difference. So let's see what we need to do. And some more space. Let's test out 2 and 2. So I guess like what do we want from this? So if we have like 0, 0 or 1, 1 for the first bit, it's okay. And then 0, 0 and then 1, 1 for the second bit. So yeah, that makes sense. Let's do 2 100,000. And then everything should be the same, or rather 2 200,000. 1, 2. Okay, now we verify that it's actually 2 to the 200,000. Indeed it is. Okay. Let's try 3. So for 3 bits, the possibility is, so we can have 0, 0, 0. Like any 2 ones, which should be 3 possibilities, and 1, 1, 1, which should be 1. So it should be 5 to the 200,000. Let's test. Okay. Actually, yeah, it was finding that fine. I feel like we have the odd case down. Even case is sort of more annoying. So let's just test out n equals 4. What do we... It's not an equal sign. What works for n equals 4? So we can have 0, 0, 0, 0, any of the 6 possibilities for 2 ones, or maybe 1, 1, 1, 1. 4, 1. That's 8. Yep, that makes sense. 1, 4, 2. Should not be 64. That is good. In fact, it should be more. So I don't know what's up with that. Why is it not more? This works. Yeah, this should be definitely more than 64. Because all of these work, no matter what. Cur equals cur times equal EQ to the I. What is EQ? EQ should be 7. So 1, 7, 49. Except the 1 is multiplied by some amount. Wait, it should be 16, 7, 49. No, that's why. Because it has to be n times that. It's 2 to the n that many times, not 2 to the that. Right. Because it's 2 to the n, and all of the bits work. Now we should get, like, I don't know, 16, no, 73? 72, okay. Yeah, that makes sense. I just made a random guess. I think 72 is right. It should definitely be more than 64. I'm gonna try again, because penalty doesn't matter. Like I said, I'm already screwing over my time by doing these explanations. Okay. As that in grid, we have n rows and 10 to the 9th columns. Okay. Moment was drawing and became interested in the minimum number of rows one needs to remove to make the grid beautiful. The grid is beautiful if there is at least one column containing a 1 for every 2 rows. Okay. For every 2 consecutive rows. For every 2 consecutive, so like this, there's at least one column containing 1 in both of the rows? I guess it is in both of the rows. How many rows are there? What is, okay. So like not that many rows. So like, cool. Well, there is the squared DP, but that, of course, doesn't work. We need to print the rows themselves, okay? If any row has all zeros, we remove it. If, let's see, some segment intersects no others, we might as well remove it. If, what else? What can we do instead of ifs? Can we actually get somewhere? And hopefully the mic doesn't fall. Hopefully the audio works. I'm just gonna keep tapping the mic because I just want to make sure that it's the mic picking up the audio and not the laptop. Because the laptop's mic is horrible. Let me close this. Row number I contains digits 1 and columns from L to R inclusive. Yeah, and they may overlap because they hate us. So what? Rows that should be removed. Yeah. It's like in this case, it is beautiful. Man, these samples, my God. Actually, it's more like, okay, so the DP that I was thinking of is stupid. There's a better DP. So ignore what I was thinking about that I didn't tell you. And essentially, like a maybe promising DP idea is, like, it's just, DP is the minimum number of rows that need to be removed, where the last row we kept is like this one. So then how does this work? Well, one row can transition to another if the segments have an intersection. I don't know what that means. Problem is it could be n squared every time, and that's bad. Okay, if we use a stupid implicit segment, why did they have to make it 10 to the 9th? If we use a stupid implicit symmetry. But let's not do that. Actually, we can compress coordinates, that'll work. Actually, that's just like straight segmentry. For whatever reason, they had to make it 10 to the 9th because, again, they hate us. And the samples are useless because they hate us, and etc. But so the idea is we compress coordinates so that instead of being up to 10 to the 9th, we like if we have a segment where it's all ones like this and then like nothing else matters, then we compress it so it's like only the endpoints of everything matters, and then it's 1 and 6, because nothing else really matters in this case. So that makes it nice, because there are 3, 5 intervals. So there are at most 65 distinct coordinates, which is an ugly number, but 2.5 seconds sort of has suggestions. Then what we need is what we're going to do is we're going to store the maximum number of rows that we do keep. Okay, so we have 65 distinct coordinates. So basically now we're going to create like a segment tree. And then suppose we have a row that's kind of like this. So it has intervals like this. Then we figure out whatever its dp value is. So dp of I. Then on the segment tree, we're going to set the value to be this, dp of I. And this is whatever it was before, and this is whatever it was before. And this is also going to be dp of I, and this is going to be dp of I. Actually, that kind of updating is kind of messy. No, I guess it's fine. It's just set it to the maximum. Well, yeah. No, what am I saying? How do we avoid segment tree beats? Let's do that. Alright, yeah, this is not what I thought it'd be. Crap. The segment tree beats would do this, but I don't want to use that because I don't know how that works. And it's like to do 2D. Shouldn't be that bad. At least I do give the explanation here. Like, this would be the idea. And then we're computing the next row, then we query the segments that we're at. And then, like, that's the maximum. You know, the problem is updating. But also, like, is it? Whoa. Because I'm going to try and invent signature beats on the fly. If we're doing maximum, we're querying maximum. I guess it doesn't matter. Now, I'm thinking about lazy propagation now. I think the operations set like this is the operations we're working with. This and this is the operation we're working with. I think this should work. Like if we're, suppose we're at this symmetry node, and then it has like its children. So maybe the maximum of this is greater, but the maximum of the children is smaller. But that's fine, because we just like, we don't push it to the parent, but we still push the update to the children. I feel like that should be fine if we do that. Specifically because it's always going to either increase or not change. I think it'll work, but like why, what is the point of coordinate compression? Why would you put that there? It's just a waste of time. We already did it for whatever the other problem was too, the one about sorting. So C into N and M, I guess. Finally don't have multitests anymore. So you can get rid of that. Push back L. PI is equal to LR. You can look at my template for what get unique is. It literally just like, it sorts a vector and it, like if there are duplicates, it'll erase them. So I templated it because I always forget what this syntax is, and it's very useful. So yeah. Rev chords I is equal to I. Now for each interval, pi.f is equal to rev pi.f. Do the same for the second. So this all is coordinate compression. Essentially, we're putting all the coordinates into a big list. We're getting only the unique ones because duplicates don't really matter. Then we're going to reverse them by saying this coordinate corresponds to this index, and then we're doing that, and then it's perfect. And because we're only caring about intersections, we don't need like in between. Like in this case, we don't need to preserve the fact that there was anything in between these, because if this coordinate doesn't exist, then no other interval has it, so if the middle doesn't really like matter. Okay, now we've done one of the annoying parts. Now we need the other annoying part, which is like the whole problem. So what is the whole problem? We need a segment tree. We need a max operation, except like also like sort of different. Okay, so in this we need to return the entire thing because it's initializing with itself. And we need to do the constructor. Okay, so this is the operation. If the other is larger, then we return that. Otherwise, we return this. Then, what is lazy of? Oh, it's just equal. Yeah. This is the same thing, actually. Don't need size at all. In fact, the whole thing is pointless, but might as well. So then this is actually op lazy I, because merging is the same thing as lazy merging, which is nice. I'm pretty sure that means we can do this. 0, -1. So first we're going to fix init. -1 means we're like, wait, is this okay? Yes, DPI will never be 0 like normally, so that's fine. It means the origin is -1. Okay, so the array is 0, so everything's 0. So we don't actually need to init at all. Like everything is going to be this. Updating. Ow! Jesus Christ. Hit my foot on the table. Alright, we don't need this part. We're just gonna mess with stuff a bit. This is not how this works. This is lazy_i.op. Forgetting my own template. Which is why I need to make an explanation of how this works at some point. I'll have 0, -1 be the sentinel. Don't need this. Null v doesn't even make sense as a name. I gotta clean this thing up at some point. This is query, op makes sense. Don't really need this. So then the op v. Does everything make sense? So 0, -1, 0, -1. We're going to do the op, then we're going to merge. As long as I didn't screw this up, it makes sense, then everything is good. Since segtree max t st.init. The array we use doesn't matter. So then IV shoot. This isn't actually a big deal. I'm not using the array here. So I'll get rid of this just for clarity's sake. So then IV AI.push back PI. So IV is just the list of intervals. So this should actually be a vector of pairs. If there are no intervals here, DPI is equal to 0, -1. Otherwise, what are we doing? So, for each interval, okay, it's confusing to use both max t and pairs, but whatever. For IBI, so we query x dot first, x dot second. If res dot first is greater than res dot val, then cur is equal to res dot val, res dot int. So we're just taking the maximum. Plus cur.f. Because now we get this row to keep as well. So then dpi is equal to cur. Now we update st.update x.f, x.s, max t for cur.first, cur.second. Okay. I guess we can do this. Yeah. Might as well, if we have all zeros, then it's better to do that. Right. DPI. Val is greater than cur.first. Don't need this. This code is a mess. It's true spaghetti code right here. Well, that's fine. I just want the answer. The answer is 2. The answer should be 3. So something's up with that. CFI. Could be the segment sheet is wrong. Like, it could just straight up be wrong. There's a non-zero chance of that, but I don't know. Why is the parent non-existent? Oh, that's why. It should be I. But why? Yeah, st.query. This is specifically because it's the coordinate 15, 15. So maybe this is updating wrong. What? What the hell is the prep? Did it not? Oh, dot val. That's 2, 0. What? What is chords? What is happening? That's another question. 1, 7, 8, 15. So what happens when I do this? I eventually want this to be 3, right? With 0 the whole time. If I do 0, 3, it'll be 1? No, it's 2. See out x. Must be something that's being messed up here. So 3, 3 is always 0. Let's do this. Same deal. Why? 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 What exactly am I updating here? So I'm going to update this to have value 2. Yep, it's not doing that. Why did it not do that? I don't strictly need to reset this. Doesn't change it. Why did that not change anything? It's gonna be a fun problem. Isn't it? It's like, this should be 0. That makes sense. What about 1, 1? Is it pushing that update right, or is it just not doing anything at all? Should be 1. Should be 2. Should be 2. Okay. Why then? Why? Like, the update should be handling this. Is it not? I'm doing an update specifically to three to set it to 2. It's just not doing that. We need this. Let's go deeper. Let's go deeper. That's a lot of stuff. Okay. So where's update 332? It's not even getting there. What is going on? What is going on here? Oh wait, that's why. Yeah, that does make sense. Okay, that's frustrating. Segment tree is not big enough. I should check that again. Yeah, now we're good. Answer here should be 2. Now we're good. Okay. Alright. Wait, how could it possibly be 0? Okay, that was annoying. Let's check everything else for that. I should not have absent-minded that. But that's good. Caught that bug. So read in NM. Up to M. Do that. Put all the things in the set. Reverse all the coordinates. Now initialize what the coordinates.size. That's the size of the signature we want. Now that makes more sense. Up to N for each row. For each interval. I don't even need this. Code's the same. Yeah. Now we should be good. Okay. Now we're gonna do restoration. So the DP is storing not only the answer, like the number of intervals we can keep, but also the or the number of rows we can keep, but also the position of the previous DP value. So we're doing, while this is not -1, while the parent, actually no, this is better. We need to do while loop because we need to do the first thing. So essentially, while this is not -1, no. No, this makes sense. Target is specifically the index of what we're at, not the parent. So if we're at index -1, then we're done. So C targ.s is equal to 1. We're using C as an indicator of whether we keep this interval or not. Then targ is equal to dp targ.s. N I++. If not ci, yeah, not C, we're going to keep that interval. Good. 2, 4, 5. Now the final step. It's n minus the number of rows we can keep. Make sure audio is working again. I think I'm talking slightly not into the mic, but hopefully it's still audible. Zero. 3, 2, 4, 5. Yep. I think I've already gone over this enough. I think we're good. I'm gonna submit. See how it goes. $14. $16. Okay, we seem good. That's okay time, I guess. I mean, the numbers are big, so that's sort of expected. All right, interactive. Awesome. And we have 50 minutes left, so I guess we'll see how this goes. You're on 8x8 chessboard. Rows are numerated top to bottom, columns are numerated left to right. Yes. Okay, just making sure. Row X, column Y. Good. One turn, you can move the queen to any of the squares on the same horizontal line. Yep. And the queen cannot stay on its current cell. In one turn, the king can move wherever. I feel like this is known. This feels known. feel like this is known. Okay. Basically, you have a queen, you have a king, you don't know where the king is, but you need a sequence that will, no matter where the king is, you will trap it. So for instance, if you're like, say the chessboard is 2 times 4, whatever. If you're like here, and the king is here, then you block this, and you block this, so they can't move. You have to have them in a corner somehow. Oh, you get the direction. Okay. What is invalid? Can the queen capture the king? Oh, okay. I don't understand that. I don't understand why this isn't super easy. So what am I missing here? Can the queen... Like, this is checkmate, so the king cannot capture the queen? So then why don't we just, like... I'm gonna copy this over. Why don't we just... I don't understand the problem. I don't think I understand it right. Because if we could do that, then the strategy is just start here. Then we sort of cut off the king, right? So if the king's here, they lose. Then we move up here. So then if they're in this quadrant, they get checkmated. Then we move up here, so that if they're in this section, they get checkmated. And then move down here, so that if they're here, they get checkmated. And we always cut the king off from moving anywhere. So I don't understand what's wrong. Chosen to control a queen, hunt down the hidden king. Move the queen. Okay, I should like very elaborately read the statement. So you can move like a queen moves in chess. King can move. Yeah, he cannot move onto the position of the queen. So he cannot capture the queen. Okay, I don't understand. I'm just gonna try this and see if it works. I don't get it. So I could just be totally wrong, or I could not be. So, so we're going to move, is it 6? 5 times. So I'm gonna reverse a bit. I'm gonna start here, go this way, go this way, go this way, and go this way. So it's 5 moves right. cur dot s plus plus moves dot push back cur. Then we're going to go that way. Then we're going to go this way. We're going to go this way. Is there like some catch? I'm gonna try it, maybe get wrong answer, and then just see how that goes. Like this seems, it feels too easy to be it, because it doesn't depend on the moves or anything. See out cur.f c and s. If s is equal to done, break. This should be endo. Right, like this is it. This is the code. So moves. I didn't read in test cases. I might look like a total idiot right now, but I really don't understand. Like, is that it? Okay, wrong answer on pretest 1. Wrong answer on pretest 2. What? What's the output? 9 moves. Why is it not pass? How does it pass the first one? 2. Suppose they were here. Then they're forced to move here. Then it's just done. Is there like stalemate? You win if the king has no valid moves. I'm bewildered. Start the game. I mean, okay. What's the sequence we use? So up to 7. Then 3, 7, 7, 7. Stay on row 7, back to 2. We go back down to 2, 2. I really don't understand. Seriously. What is this notation? Why is not equal 4? Okay, sure. That's such notation. Anytime the king can move, so he doesn't get out of the board. So if he's on the queen immediately, he's trapped. King is on square 4, 5. Place the queen at any location on the board. He's done once per game. So you win the game, run out of moves. You win if the king has no valid moves, which should count stalemate. It doesn't say anything about captures. In each test case, you should print the queen's starting cell immediately. Maybe the strategy? I mean, okay. So if the kings... So if the let's look at the possible locations of the king, right? So if the king's in here, I will get him by moving this way. Now, maybe the king was in here. Then when I make this move, the king is forced to be on... Oh, wait, that's how that works. Okay. Right. Okay, never mind. If I move so that I'm... Okay. Yeah, that makes sense now. I'm just being dumb. Okay. Just gonna say chess. I also feel like this is a thing. Okay. Alright, this makes more sense now. I think I was being dumb. Forgot the king can move over the boundary. Right, okay. So Now we actually understand the problem. Now we think about what we need to do. So we can't actually find the position of the king. We just need to find like where they are relative to us or something. Find the position it's over. If we're adjacent to the king at all. Suppose we start off by like moving ourselves at the bottom. So maybe we start off here and then we like do that. Then if the king is spawned anywhere, if the king started anywhere on this row, then it's done. And then what? And then if we start like anywhere higher, let me get rid of this now. You know, the problem is like this isn't a wall. Like if I move here and the king's here, then they can step over to where the queen was, and that doesn't work. I feel like I'm gonna do some more Googling. No. Okay. How do we like... Can we force the king back a row or something? Like if we start off somewhere, can we do a sequence of moves that forces the king to move back a row? If we can do that, then we're good. Then we win. So somehow we just do that. Suppose we like start on the bottom row or something. What if we like do this? If we start off here and then sweep this way. So if the king is somewhere, this is kind of tricky. So my new idea is, if we get the king right below us, then the only two squares they have to move are here and here. And in either case, then we force him back a row, and that's what we want. Because if we can force him back a row, and we do that 7 times, then we win. Now the question is how to force him back. Well, how to detect if we forced him back. How much is 130? $21 times 6 is too much. Barely too much. We're gonna start ourselves off. So we're gonna start ourselves off here. And use blue for queen, red for king. So if the king is on this row, eventually he will move back. If we ever detect that he moves back, then immediately we advance. Right. If he ever moves back, we immediately advance. What else? What if he never moves back? Actually, if he never moves away from us. If he never moves away from us in the time that we go here, that means he is not on this row, so it means we're good. The problem is if he moves towards us, then it's sort of harder. What else can we do to ensure that we win? So the issue I'm thinking of is like, so we're doing this. Maybe he like starts off here and then he never moves back, and then eventually he moves into this row. And that's the problem. because to get the information, when we try to get information, the information changes. So it's very possible that the king could do that. Could move into that row that we're in. And then we're a bit screwed. So again, if he never moves vertically, we're good. If he never wait, how many times can that happen? That's the thing. Okay, if he moves this way and then he never moves back, then he's one step closer to us. And that took 7 moves to make that happen. Maybe 8. 7, yes. So then, how many times can that happen overall? Well, if he ever moves back, or if he ever doesn't move, we know we can step forward. So every time he moves towards us, we don't step forward. But that can't happen that often. Specifically, it can only move towards us 7 times and away from us 7 times. Okay, new plan. I have a decent amount of faith that it will work. So, alright. See ya. Test cases. I'm gonna use go-to statements. Go to done. Move 1 1. Okay, so LR is equal to 1, while R is less than 7. If C is not equal to 1, move C R1. Okay, now two I less than equal to 8 I plus plus. Move Ri. So if he moves down at all, R is equal to down, or R is equal to down right, or R is equal to down left. That R is a terrible variable name. So if this result is any of these, then we win. Plus plus R, break. If, okay. So if res is not equal to right and res is not equal to left, then it is a vertical move. If ver is equal to 0, plus plus r. Let's see. What? Come on. Alright, fine. Okay, so 1. Right. How are we on 2, 2? Oh. C is equal to I. Move r plus 1 C. Says scam likely. I guess that's the thing to take. Okay. Shoot. 1. To type these out exactly. Okay, so we moved to 2, 8. Right. Okay, so up. Right, 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 left, left, left. So it should stay here. Good. Right. A better idea. I'm gonna start on 8. Okay. Okay, I need to change the structure of this code. Okay. I'm going to structure it this way. So we're going to determine if we want to move down. While good. C. If C is not equal to 1, is equal to move R8. A lot of edge cases here. I think this should work though. Essentially, every time we get it down, we just keep moving down. String res. Res equal done, return. Yeah. Slap that everywhere. 1. So left, left, down, left. Down, down, left, down. These moves probably don't make sense. I'm just putting random things in. Left. Okay, so 1. Okay. Two. Okay. So while good, yeah. Take two. Pretest 8. Nice. Alright, that's over. That was cool. Yeah, so like I said, I was not going for speed in the slightest. You saw me like very elaborately going through solutions and stuff like that. So overall this is pretty cool. I like the last problem actually. I very much feel like I've seen it before. There's no way I haven't. Like I've definitely seen this problem before, or something like it. Just like you have an unknown king, you have to trap it somehow. You have to create an algorithm to trap it. But I don't know. So yeah. But I guess like, whatever. That's pretty cool. Penalty's horrible, but that's fine. Again, the whole point was to just either try and solve everything or be elaborate in how I'm figuring out the problems. So this one was pretty cool. It was sort of like a logic. It was you're trying to just like create an algorithm to trap the king, and the main idea was like you can't. So like we're going to move down. We're going to try and get the king on the last row. Because if we do, then we can, like, if we're here and the king's here, then we're done. We just move along this way and he will eventually be mated, no matter what. Or stalemated. Some form of mated. But the problem is, suppose the king is, like, here. Then if we move down here, the king can move up here. And we're trying to trap the king down here. So now we're, like, never going to trap him. He can always evade us because we think the king is, like, down here. So we need to make sure that every time we move down, we guarantee that the king is never directly below us. And so that's what the strategy is. That's what my plan was. And then the implementation is figuring out how to make that work. That's the main idea of what just happened now. And it's just kind of a lot of casework, but it worked out. Did I ever like... I don't think I've ever had this like in an actual bracket. I think it's always been like that. But yeah, I'll say that was a fairly cool problem. Even though I swear I've seen it before. I swear. You got some pretty bad penalty because of that. Because of like not rushing. I don't know, A was kind of like, kind of tripped me up. Like it's sort of intuitive that you want to put the bigger one by itself, but like not that intuitive. I mean, yeah, I don't know. I didn't trust the intuition with that. That seems to just be like you move an element from the smallest into the big one, and it worsens the answer. Yeah. Okay. I guess we're done. Ignore this. This was some dumb mistake. This was also a dumb mistake. So overall, I guess I can talk about my opinion on all the problems. I don't know. I don't think I do that much. But okay, this one was okay. Made me think of it. This one was sort of felt maybe easier than A because I had a hard time with it, but the solve counts say otherwise. But like, I think it still had some ideas at least. Like, what are you forced to do, and then yeah, like what are you forced to do? This one was like, it was okay. Just work out some conditions and then count them. Some combinatorics involved. For this one, I don't really understand what the intended was. I want to look at the runtimes of some people just to see. Pretest 4, pretest 4. Okay. And I could like look. Fine. E, D, verdict accepted. Yeah, pretty chunky runtimes overall, and mine wasn't that small either. So that's a thing. And then this one was, I like this one. Eventually. And then, yeah, this one was sort of just like, it was just like a do it problem. My rank's gonna go down because my penalty was really bad on the first 4. So that's fine. Contest's almost over. I could definitely make top 20 if I tried more, but that is okay. So how are my friends doing? Well, he's gonna get master again. That's pretty cool. I'm just stalling because I don't want to do solutions yet, but I don't really know why. Everyone but Aaron is getting plus. He's just dragging everyone down, as always. That's a joke. Okay, I don't think I have more to say. Let's do the solution part. You should be good on the microphone. Yeah, okay. I'm tapping because if the microphone's like really like focused on this point. So if I tap right on it, then it'll make a strong noise. And if I tap on the laptop, then it won't pick it up nearly as well. So that's the test. Because if I tap on the laptop and it's on the laptop mic, then the laptop should theoretically pick it up more tapping on the laptop than tapping on the mic. Also, I like tapping on the mic. It's kind of fun. Messes with your ears. You're welcome. So right, so for problem A, essentially we have a list. I'm gonna have to refresh all these pages soon. We have a list, for example, like 1, 2, 3. We're going to break this list up into 2 lists, however we want. For example, we could have one list be 1 and 3 and the other be 2. We can have one be 1 and 2 and the other and 3, and so on. Or 1 and 2 and 3. In fact, these are the only possibilities. But the point is, every element must be in one of the resultant lists. So what we're going to do is we're going to break them up into the lists, and then we're going to take the average value in both of the lists. In this case, the average value is 1. In this case, it's 2.5. Then we add them together, and then that's our like score for the 2 lists. We want to maximize the score. So how do we want to print the maximum score? So in this case, the best thing we can do is anything, actually. No. That is not true. The best we can do is put 1 and 2 in their list and then 3 by itself. And then in this case, the score is 1.5. In this case, the score is 3. So the total is 4.5. They do enumerate the different ways to do the thing. So like in this case, you get 4.5, 4, 3.5. And in general, the best way to do it is just by looking at the sample, first of all. And by looking at the samples and doing that. The best thing you can do is to put the largest element in a group by itself. So for example, we have 1, 2, 3, 4, 99, 137, 6, right? So the best thing to do is to isolate the largest element, put it in a group by itself, and then and then have everything else be another group. So the intuition sort of behind this idea is that when we put the biggest group with some other elements, the biggest element is going to be sort of watered down. We sort of want the smaller ones to be watered down. Like we want these and maybe this one to be watered down because like they're not as big. And by watered down, I mean like the average, somehow I'm on erase mode. The average is equal to the sum over the count. So if the count is larger, then the denominator over this is going to be much bigger. In this case, the denominator is 1 here. So we definitely want the denominator on this to be small. And so in general, the best way to do it is to have this denominator be 1, and then we sort of screw over everything else. And so this is our answer. For a more formal proof, you can think of it like, say we start off with this configuration. Then we can show that from here, we can't make the answer better. Say, for example, we move the larger element over. Then this decreases because it loses the largest element. So this average is going to decrease. And this average also decreases because 99 is watering down the 137 now. So it's definitely not a good idea to do that. And you can show that like in any case, it's always going to make the answer worse or not change it. And then I guess you can like, from some other starting configuration, you can also prove that it's better to move it towards this. Crap. Every time the mic moves. I'm scared for my life now. Yeah, that's the basic idea. If you don't exactly understand why that's true still, I'm sorry, I don't really either. I just sort of proved it and then it made sense, but the intuition's like sort of there, but it's not like fully for me, so I'm not sure. Maybe the editorial has a better explanation, but that's the way I thought about it. For this one, you gotta. So let's say, the way this problem works is we have a list, something like this, 3, 1, 4, 2, 5. This is a bad test case. Let's go back to the 1, 4, 2, 3, 5. Right. So we have a list. Yeah. So what we're going to do is we're going to split this array into at most k. It says exactly k, but it doesn't matter. It can be at most k. Different subarrays. So for example, if k equals 3, we can split like this or something like that. And then we're going to reorder these however we want. And then, so maybe for example, we move 2, 3 here, and then we don't touch the 5. And so we have 2, 3, 1, 4, 5. And then after we do this, we want the array to be sorted. So we want to determine if it's possible to do this. So suppose like k equals n, right? Then we can break everything out. We can break everything up into its own subarray, and then we just sort it. So that would work. But sometimes k is smaller. And so the question we're asking is k large enough for us to be able to do this? So a different way to think about this is like, how many subarrays do we need to sort it? So consider some group like this. For example, we have 2, 3. 2 and 3 are right next to each other in the final sorted array. So there's no reason to split these two apart, because in the final array, they're going to be next to each other anyway. So we might as well leave them next to each other. But all of these other pairs of adjacent elements, 1 and 4 are split apart. They need the 2, 3 between them. And 4 has to be after the 2, so that's definitely not possible. And 3 needs the 4 between itself and 5. So all the other positions, they need that. They need the split between them. So we need at least 4 subarrays in this case. So if k is not greater than 4, or if k is less than 4, then we can't do it. And otherwise, we can do it by splitting into 4. And if k equals 5, we simply we do more splits, except we just sort of ignore that and treat them like they're together. So the exactly k doesn't really matter. It's just at most k. And let's take some other array. I'll just keep doing this. 4, 1, 2, 3, 5. Here, these will be together. These will be together. This will not. This will not. We need 3 subarrays. And if we have something like 1, 2, 3, 4, 5, then it's already sorted. So any value of k works as long as it's at least 1, but k is always at least 1, so it's fine. So really, how do we count these subarrays? We're asking for each pair of adjacent elements, are they together in the final sorted array? Which is actually not that easy of a question to ask, because we have negative elements, we have like huge elements up to 10 to the 9th, but they're all distinct. But still, like, it's kind of messy. So what I did was for each element, suppose we have, for example, 1, -4, 0, and then 2. What I did was I found the position in the sorted array of each element. So in this case, this is position 1, or 0, if you 0 index. This is 2, this is 3, and this is 4. All right? And then we're treating it like this. So now we can directly check if this plus 1 is equal to this, then these elements should be next to each other. And so it's okay to have not a subarray between them, or a split between them. And then here they have to have a split, here they have to have a split. So the hardest part now is finding the positions in the sorted arrays. And the way I did this, I did this in my code. Actually, I should have gone over my code for A too. I did not do that. I will do that after. But yeah, sorry. So the way I did this was I created a new list, which essentially stores a pair of value and index. So value index. And then, so for example, this is -4, 2. This is, you're gonna have to excuse my brackets, I'm lazy. This is 0, 3, and this is 2 and 4. Then we're gonna sort this list by the value. So this would become 0, 3. This would become, nope, sorry, -4 is first. This would become -4, 2. This would become 0, 3. This would become 1 and 1, and then 2 and 4. Now we know that this is the sorted array. So these are the positions we're interested in. So now we know that the element in position 2 of the original array is position 1 in the sorted array. So now we can assign 1 to this element. Similarly, we know that the position 3 in the original array has position 2 in the sorted array. So we assign 2 to this one. We know that 1 has 3, so we assign 3 here, and 4 has 4, so we assign that. And that's how we get the information we need. Mouse. So code-wise, this is how that works. Read in the stuff, create this list of pairs, sort it, and then this B is like the location in the sorted array. So I'm saying the value of B at the index in the original array is equal to the index in the sorted array. That's what this statement is. This statement is like the crux of the coordinate compression, which is another word for finding the position in the sorted array. It's called coordinate compression. In fact, we'll use it in D. So yeah, that could be relevant. And the final part is saying, checking if they're adjacent to each other. So if this is 1 greater than this, then it works. And because it's distinct, it's like fine to do that. And the answer must be at most k minus 1. And the reason it's k minus 1 and not k, which is something I got this wrong answer for, messing up, is do they have 2 samples? No. The reason it is this way is because we're counting the number of splits we need to make. But we're restricted to k subarrays, which means that we can have at most k minus 1 splits. In this case, we have 4 subarrays, but we have 3 like divisions between them. So that's why it's k minus 1. Yeah. Because I forgot, I'll go over the code for A and then put that in its own timestamp. So basically, read in the input, sort the array so that the largest element is at the end. And then for everything but the largest element, take the sum, then divide it by the count. That's just definition of average. Then directly add the last element because it's by itself, and that's the answer. Be sure to use doubles instead of integers. And a sort of technical detail is using set precision, because otherwise, if you print like 1,000,000, then it will print as 1e6. For for example, or anything that's like greater than 10 to the 6th or like 6 digits of precision, it'll not be nice. And so like sometimes Codeforces will judge that correctly and sometimes it doesn't. It depends. I think it doesn't actually, but some graders do. But just like don't risk it. What you can do is you can do set precision, so that'll make it so it'll print to 15 like decimal places. Usually some people use the numbers like 12 or 10 or something like that. It doesn't matter that much. And fixed means it's never going to be in scientific notation. It's always going to be printed as like just a number like this. Yeah, so the way to determine like how much set precision you need is like you look at this, and then like if it's 10 to the negative 6, then like generally just print like a bit more than that. So maybe like 9 or 10 would work for this problem. Yeah. Anyway, that's B. C is like, it's gonna be a pain to explain. Like always, I'm not great at explaining bitwise problems, so this is gonna be fun. First, let's go over how I understand bitwise AND and bitwise XOR. So bitwise AND, bitwise AND is going to return, actually first of all, first things first, consider each bit separately. Can't write. I'm not even sure that's how you spell that, but yeah, we consider each bit separately. And then, so for example, like in the context of the problem, this would be like assume k equals 1, just to start. Because bitwise AND and bitwise XOR is bitwise, which means that it goes bit by bit and applies the operations, like the third bit will match up with the third bit. That's what bitwise means. Which means that all the bits are sort of independent from each other. Almost. The problem is this greater than or equal to, but we'll deal with that later. So for now, it's just assume like k equals 1. So bitwise AND is 1 only if all of them are 1. So if we have 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, because we have this 0, it will return 0. And if it's all 1s, then it will return 1. That's the definition I'm using for bitwise AND. And for bitwise XOR, it's 1 if there are an odd number of 1s. Which is sort of how it's defined. Formally, it's like it's addition modulo 2, which is the same as saying if there's an odd number of 1s, you get a 1. If there's an even number of 1s, you get a 0. So for example, like 1, 0, 1, 1, 1 would be 0 because you have an even number of 1s. If I do this, we get a 1. If I do this, we get a 0. If I do this, we get a 1, so on. And of course, these are all like, this isn't a number. This is all like XORed together. And the same for bitwise AND. Like assume these are all XORed together. You're welcome for those drawings. And sorry, OCD. But yeah. So this is how we're doing this. So then when is a single bit of the AND greater than or equal to a single bit of the XOR? And when is it less? Well, suppose we don't have all 1s. So not all 1. Then the AND is 0. So for this to work, we generally need the XOR to be 0. So when is XOR 0? Again, even number of 1s. So this bit, so that's how we do it for XOR equals 0. And for the AND equals 1, the XOR depends. It depends on the number of bits we have in total. So it's 0 if n is even, or 1 if n is odd. So this sort of matters though, because like when n is odd, when the AND is 1, the XOR is always 1. So no matter what, it's never the case where the AND is greater than the XOR. The AND is always less than or equal to the XOR when n is odd. Which means that for each bit of the AND must be equal to each bit of the XOR for odd. Like the total AND must be equal to the total XOR. And the only way to do that is to either have this condition true or this condition true. So in what cases are these conditions true? So the number of ones must be equal to 0, for example. It has to be an even number, or 2, or 4, or any of those up to n minus 1. This is specifically the case where n is odd. So that's how we satisfy this condition. So any of these works. Any of these work. So as long as we have this number of zeros, we're fine. And, or it can be n, because in this case, the bitwise AND is 1 and the bitwise XOR is 1. So the answer for odd for a single bit is the sum of n choose 0 and 2 and 4 and etc. up to n minus 1 and then n. So it's the sum of n choose 0 plus n choose 2 plus n choose 4, etc. That's for a single bit. And because each bit is independent and each bit has to be the same sort of property, it has to be equal or not. It has to be equal. Then we're going to raise this to the power of the number of bits because we have this many choices for each bit. So this is the answer for n odd. In code, that's all I'm doing. The odd code is much simpler than even. We're basically just summing this up. N choose n is 1, so that's why I started off as 1, and then it's just summing the even numbers. And then we raise that to the power of k and print that. The even is more annoying. I don't know why they didn't, they had to do casework, and I'm convinced these setters just hate us. They made samples garbage. They made all the casework happen. They just, they made you do coordinate compression in D. They just hate us, man. But n being even is basically it's the real thing, but it's also I guess not that much of a stretch when you get this idea. So the difference here is this. When everything is 1, the bitwise XOR is equal to 0. Which means that here, the bitwise AND can be greater than the XOR at a bit. So what this means is that when this happens, all the smaller bits, we don't care about them anymore. Because we already know that this is greater. So no matter what, as long as the bits above are okay, these can be anything. Because just imagine you're comparing 1 to 0, and you have 1 0 0 and 0 1 1. Because this is greater, all the other bits, they cannot match the power that this one digit has. So, that's how that works. It'll be 4 is greater than 3, which is true, of course, in decimal. So how do we count this, right? What if we have multiple of these positions? How do we quantify anything? And the way to do it usually is we're going to focus on the first time where this happens. So specifically, we're going to create a structure of a number. We're going to create a structure of an array like this. So we have a position where AND is greater than XOR. And this is specifically the first position where this happens, meaning that everything above has to have AND less than or equal to XOR. But it can't be less because it has to be greater than or equal. So it has to be AND equals XOR. And anything below can be anything. So where can this first position be? Well, it can be anywhere. So let's iterate over it. It can be from 0, I'm 0 indexing now, just to make that clear. From I equals 0 to m minus 1. It can be anywhere in, or not m minus 1, sorry, k minus 1. I might have to make that distinction. If you think I made a mistake in distinguishing n and k, I probably did. So feel free to override me anywhere if it doesn't make sense. But yeah, so we go from I equals 0 to k minus 1. And also, there's the chance that this never happens, in which case it's sort of considering it like I equals k, because at this point, everything is equal, and then we never get this position. So we have k positions where this is true. So in my code, that's why I iterate up to k instead of excluding k. Because it considers the case where this never happens, and it's only this the whole way. So, so how many ways do we have to do this? Well, we sort of already figured that out from the odd case. It's anything where the number of ones is equal to 0, 2, 4, etc. That's not a 4. 0, 2, 4, etc. up to n minus 2. And not n, because n would be this case. So only up to n minus 2. So it's the sum of n choose all of these. And choose that. That is a fat binomial. Yeah. And then all that to the power of, not the power of k this time, but to the power of the number of things we have here, which 0 indexing is I. So this is to the power of I. How many ways do we have to do this? Well, this is all ones. It has to be all ones. So there's only one way to do this. And what about this? Well, because it's anything, each position here can be 2 to the n. So in total, we have 2 to the n, 2 to the n, to the what? In this case, the indexing here is k minus I minus 1. You can work it out by just like looking at a small case, or the fact that, this has to be an I. The fact that this plus this number plus this 1 has to be k, because that's how many positions we have. So you can solve for this number, and it turns out to be k minus I minus 1. So then the answer is the product of these three, but this is 1, so it's just the product of these two. And that's the answer for this I, and then we sum that up, and that's the answer. Because we're accounting for all possible first positions where this happens, and also they're independent because the first position is unique, like it uniquely defines a sequence. So we're not overcounting, and we're counting everything, so it's a valid way to count. So in general, it's the sum from I equals 0 to k inclusive of this entire thing. This is gonna look dumb. It's the sum from I equals 0 to k of this entire thing. And yeah, that's the answer. Code but make more sense to read, so here you go. First, we count the number of ways for it to be exactly equal. It's, in fact, the exact same code as odd. And then for I equals 0 up to k, we first count this part. It's the power of this, which is the variable eq to the I. And then if this is valid, then it's 2 to the, this is also saying 2 to the n times k minus I minus 1. In my code, I forgot the n. Don't do that. So keep the n. It's 2 to the n times k minus I minus 1, not 2 to the k minus I minus 1. So multiply those together, add that to the answer, and that's it. Samples are garbage. Yeah. I don't know how this would fail system tests, but maybe it could, so who knows. Have there been system test fails? Doesn't look like it. And people have solved, looks like he forgot to register. Nice. I have had that happen before. Maybe there's an easier way to map this out. I don't know. I'm just like, yeah, I don't really know. I guess like, maybe. I'm not the strongest at math, so I wouldn't be able to come up with the super elegant techniques, but this works. It's messy, and it relies a lot on bitwise knowledge, but it works. next problem. Okay, I'm gonna take, yeah. Never mind. Let's take like a second to recuperate from whatever that was. So we got like a sort of infinite, but like not, but like infinite grid of like n rows and 10 to the 9th columns. So it's not really infinite, but it's like a massive grid. And it has the digits of 0 and 1, so it's binary, just like problem C, but it's not like problem C, so don't fret. We're going to remove some rows so that this certain property holds. And basically, a grid is beautiful if for every row, let's consider we have rows like this. For every pair of adjacent rows, so for example, suppose we have like 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, right? So the grid is beautiful if we look at every adjacent pair of rows. And they must have a 1 in common. So this pair is good because it has this 1 in common. This pair is good because it has this 1 in common. If it has multiple 1s in common, that's fine. This pair is not good because it doesn't have 1 in common. And this pair is not good because it doesn't have a 1 in common. This doesn't have any 1s. But if we removed this row, then this pair would be good because it has 3 1s in column, and that's in common, and that's at least 1, so that's good. So we're interested in the minimum number of rows we need to remove to make the grid work. Like it has to be good for every adjacent pair of rows, and that's defined as beautiful. Right, so the first thing I jump to is DP with a segment tree, because I come from Usico, and that's the way we handle things there. So that's the solution I have. So it's DP using like dynamic programming using a segment tree, which I have a topic stream on. Yeah, so you can look at that if you want. Also about topic streams, yeah, that's a thing. That's probably happening. I'll give it like the standard soon TM, but. Okay, what was I saying? How do we solve this problem? Let's do some DP. Let's first just think about the n squared. So DP of I, and also we need to restore the answer, but like don't worry about that for now. Let's just minimize the number of segments we remove. And that's equivalent to saying we're going to maximize the number of segments we keep. So how many segments can we keep from the grid so that it still satisfies the property? How is this still in queue? I guess I submitted late. So dpi equals max number of kept rows of the rows 1 to, or 0 to I, where I is kept. This as a sentence makes no sense, but you know it's the variable I, so it works. So basically, how do we compute this? Well, essentially, we have this row I here, and we have some previous rows. So we're going to look at what was the last row that we kept. So for example, suppose it's some row j. It only works if these two rows can be together, and that's only if they have an adjacent 1. So either we don't keep any row at all, in which case I is the first row that we keep, 1. So that's the base case. But it can also be, if we keep some other row, 1 plus dp of j, if j is valid. So 1 plus dp of j if j is valid. And like, that's good because what is it? Why is it good? Yeah, it's 1 plus dp of j if j is valid, like if they share a 1. I got sidetracked, totally. So if they share a 1 somewhere, then it's valid. And it's like the maximum of this. So it's the maximum over all dpj where we can share a row. If you want, you can also add like an auxiliary row. Well, no, that doesn't make sense. Never mind. See this? What just happened? It just came off. You see this? Hope that like didn't break it. I didn't did I do anything? Okay. Still works. I guess we're fine. So yeah, I'm not getting anywhere. But this is the basic idea. Of course, this is naively this is like n squared and a bit more because like we have to check for each pair of rows if their intervals work. Actually, it's n squared times m squared by some graph theories, not graph theory, just like some stuff. But the point is, it's not going to pass. So we need to speed this up. And the hard part is like validity is weird. Like the validity is if any of their intervals intersect. So going through each interval and finding the places where they intersect is not going to work because that can also be n squared. Like suppose every interval is the interval 1, 1. And then they have like randomly scattered. Then you'll have to like, and like the places that have intervals are randomly scattered. Then it's just not going to work. Like you're going to have to sum over n squared things, like somehow. But what we can instead do is, so we cannot find some way to take the maximum over rows. What if we don't think about rows? What if you think about columns? So now the idea is, suppose we have, let's consider this again. This is a fairly large example. So let's compute these dp values. This dp is 1, this dp is 2, this dp is 3, this dp is 1, this dp is 4. Of course, because this can rely on this can rely on this relies on nothing, and this relies on that. So instead of thinking about rows, we're going to sort of push this value out to columns. And the way this works, again, because it's up to 10 to the 9th, it's given as intervals. So this is like, you get this interval of length 2 that represents the 1s and so on. And they can intersect, which is also a different way they hate us, but it's like, it's not that big a deal, I guess, so it doesn't matter. So essentially, we start off with like, we're going to create this representation. We're going to say, the best value you can get for some column that has a 1 here is 0. Because initially everything is 0. So now we're going to look at this. We're going to look at this interval, which corresponds to this. And we're going to say, if we have a 1 here, the best column that also has a 1 here has value 0. And the same for here. The best column that has a 1 here has value 0. So this dp is 1. But then now we update these values. And now because we have a 1 here, we can say the best dp value where a 1 is at this location is 1. And the best dp value where a 1 is at this location is 1. Then we continue on to here. Now for this one, we look at the 1s that we have. So there's no value where the 1 is at this location. But we can share a 1 over here for this one. And this is 1, so we get whatever this dp value is plus a new row, so that's plus 1. So this dp value is the maximum of all like rows that it can share with, plus 1, so it's 2. And now we update once again. We're going to say, like the best we can do here is, yeah, the best we can do here now is 1. because now we have a 1 here, and the best we can do here, no, sorry, the best we can do here is 2, because if some column is going to have a 1 here, then it can be compatible with this row, and this has dp value 2, and the same for this. Now we go along here, we do the same thing. The best we can do is we can get the 1 from here, we can get the 2 from here, or we can get a 1 from here, but the best thing to do is 2. So now this dp value is 3, and then once again, any row that has a 1 in any of these columns will be able to get a dp value of 3. So now this doesn't affect this at all because it doesn't have any 1, so it's automatically 1. And then this will look at this whole thing, and because it shares something with a 3, then everything gets changed to 4. And that's sort of how we do this. So of course, naively, this is worse. This is O of n times 10 to the 9th, which is horrible, but we can do better. And again, the main idea here is to represent like best dp value among rows with a 1 at this position. So having 5 by 5 is actually a bad idea. But like if we had an extra column here, then this would have like an extra column too. Like this is columns. Probably should have defined this beforehand, but that's how it works. So how do we do this efficiently? And my answer is, as hinted before, a segment tree. First, because values up to 10 to the 9th, we have to compress coordinates. And the idea for doing that is very similar to problem B, so you can refer to that. Or essentially, we're going to find the position in the sorted array, and then we're going to compress it so that there are at most 2 times m distinct coordinates, which is 6 times 10 to the 5th, which is not a great number, but it's fine. So we're going to compress the coordinates so we can put everything in a segment tree. Now we do put in everything in a segment tree. And the segment tree operations we need to support is set A from I between L and R to maximum of AI and X. This is the update because we're going to say like everything, for example, everything in these two, everything in this interval can be at least 3. And everything in this interval can be at least 3. But we can't overwrite it because there could be some cases where overwriting is bad. Like for example, suppose we have maybe 0, 1, 0. Wait, hang on. Actually, is there a case where overwriting is bad? I think so. Actually, no. No, there should not be a case where overwriting is bad, actually. Because no matter what, if we can reach a value, then it's going to be 1 greater than that value anyway. So overwriting is always going to help. So actually, we can just have... this might be easier. We just set this directly to X. Because like when we can reach a value, we're going to increase it by 1. So it's always going to be greater than whatever the previous value was. So we can just set it to X. Right. But I did maximum. Either way, it works. This is not as hard as segment tree beats because we're asking for maximum specifically. Or, and the query is just range query, like ask max of this, like some interval. So this can be very much done with a segment tree, and that basically settles it. That's how we compute the values. And the way we restore the answer then is every value we keep, we need to keep, and then we get rid of the rest of them. So the way I did this was, instead of storing like actual maximums here, I stored like a pair of dp of I and I. And then taking the maximum, it would also maintain the index. And that way, for like the final row we're at, we know the previous row we kept. And for this row, because we know the DP value, we know the previous row we kept, and so on. And we know the previous row we kept. So we can use that information to restore the rows we kept and then get rid of the rest of them. In code, again, it's sort of different from the set idea, but using either range, like set all of these values to X, or like setting the maximum. For example, here, I just like had lazy I be like maximumed. Combining lazy operations is like saying maximum. Like to combine two lazy operations, you take the larger of them. And yeah. Anyway, it just depends on how you implement it. So assume the segment tree is a black box now, it just works. We read in the values, we do coordinate compression by creating the list of the coordinates, then getting only the unique ones, and then like creating a reverse array where we can say like the position of this value in the sort array is this. And then we use the reverse for everything so that we get the positions, like the compressed positions. Then we create a segment tree with the size equal to the number of coordinates. That's important. Don't make it n or m. That's what I did. And the answer will be initialized to like 0. And -1 is like a sentinel value. That means like we're done here. You don't strictly need it, but I just use it. So then for each row, for each interval, we query the segment tree for the best value among having ones in that interval. And then we take the best. Then we update it. Also, we add 1 because we should. And then we update it. And then we take the best like DP value as our answer. Then we start here. We go backwards using like the parent. Like basically we know this was the previous row, so we go backwards until we hit a -1. And then we mark all of these rows as rows that we keep. Like keep all of these. And then this is not kept. So everything that's not kept is removed. And that's how you figure out the answer. And it works, and it has 300 milliseconds more runtime. So that's cool. How was I doing? I assume I was doing like rather badly before getting this problem. Yeah, it wasn't. The penalty was not the best, but as I said, that's sort of on purpose. Last problem. This was cool. I think it doesn't require much technical knowledge. It's just like it's interactive. You just gotta figure out a strategy and make it work. So, in fact, I usually don't solve these, but I guess I did this time. Essentially, you have a chessboard. You have a queen, and there's a king. You don't know where the king is. I'm going to copy this one again. Ignore the pieces here. We're going to disregard them. We're going to say blue is queen and red is king. So you have a queen and a king. They move just like normally like chess. Like queen can move anywhere like horizontal, vertical, or diagonal. I think that's all 8 directions in a messy way. It's easier to draw it like this, but whatever. So, and the king can move to one of its 8 adjacent cells, but of course it can't move off the board. Your goal is to mate the king, either checkmate or stalemate. Basically, your goal is to make it so it cannot move anywhere. So the king, it cannot move into any place that the queen could move next, essentially. So the queen sort of like guards all of these spots. It guards all the spots. Like if you know how chess works, this makes sense. You just can't move it into where the queen is or where the queen can move. The queen guards all these spots. So all these spots are like on fire or something. So like the queen has like a evil laser eyes and they like set everywhere she can see on fire. And then the king can't step there. So in this case, the only valid move for the king is here. He does have to move every time. I switched the colors, and I'm sorry for that. I'm going to go back to the original colors afterwards. But red makes more sense for laser eyes. So yeah, so the king cannot move onto any place that the queen can see, and they cannot move and they have to move a cell. They cannot stay put. And the queen can also not stay put. So there's one part here that does differ from chess. It's that the king cannot capture the queen. So say the queen is like right next to the king, and the king's here. The king cannot capture. That is, this is a winning position for the queen. The queen wins here because the king has no valid moves. Because everywhere he can go is under watch of the queen. Similarly, this is also a winning position, even though it's considered a stalemate in normal chess, because the king has no valid moves. So you do have to pay attention a bit to how this works, because it is not the same as normal chess. So the way this game works is, you control the queen. You can go anywhere you want. And the king is like there. I feel like my tongue is bleeding. You can, I hate that. You can go anywhere. Like, sorry, you control the queen, and the king's there. He's somewhere. He's controlled by the interactor. You don't know where he is. So basically, you choose where to put down your queen. So for example, here. And then the king can be like literally anywhere. So the way the game moves is the king moves first. Then you move the queen anywhere you want. You also, it tells you the direction in which the king moves. So if they move up and left, you'll get a thing that says up left. But you don't know the actual coordinates. You don't know the position. You do know the coordinates of the queen because you control her. So the king moves, then you can move the queen wherever you want. So for example, the king can move here, and then the queen can move here. Which is a lucky guess, of course. Like, there's no way you would know the king's right there. But then the king can move here, and then like the queen can move here, and then the king can move here, and the queen, no, the king cannot move there because that's laser eyes. Then the queen can move here, and then the king can move like here, for example, and then he can't move anymore because the queen moves there. So that's the point. So now the queen laser eyes all of this and everything else, so the king has nowhere to move, they can't go anywhere, so they're dead. That's how a game would go. And you would win if that happens. If you go 130 moves, which is actually like a rather small number, without winning, then you lose. So you can consider it like a 50 move rule on steroids. I think it's 50. I don't remember. I don't know that much about chess. But so how do you do this? So my initial strategy was stupid, and I didn't realize like it was totally wrong. But if you happen to think about the strategy of like dividing it into quadrants, and then you move into this, maybe I'm like the only one who did this, but if you go like this and then like this, and the idea is that you mate the king like wherever they are, because you always force them into the corner, it doesn't work. Because suppose you're like here. Suppose you're here, and then you move up here, and the king is here. Then maybe the king was in this quadrant initially, but when you move up, then the king can move down, then he can change his quadrant, and then he won't be trapped, and then you'll lose, and then be sad. So that doesn't work, in case you thought of the same thing I did. But the second strategy I did does work, I think. Pending system tests, but I'm pretty sure it works. No, it's actually running right now. You guys want to watch that happen? Nice. Alright, so that worked. Basic idea is we're going to go step by step. Let's think about the final position. Suppose the queen is here and the king is on this row somewhere. Like, for example, here. Then all we have to do is go this way. Because the king can never move up, because the queen is laser eyeing the whole row. And eventually, the laser eye like wall of death is going to approach the king and then trap him in a corner. Like you have a wall of death here where it's like these 3 squares next to the queen. So if you can get your wall of death to kill the king, that would be awesome. But we have to bring the wall of death down, and we have to trap the king on this row. So how do we get ourselves on this row and the king on this row? Let me move this over. Let's think about how we do this. Let's start on this row. And then the king can be like anywhere. Suppose they're here. And the main idea is if the king is on this row, we're going to move, actually, I'm going to move this way. Suppose the king is on this row. On this turn, the wall of death is here. If the king is at this position, like the queen will guard these. If the king is at this position, they must move down. And if the king moves down, then we can move down too. The only problem with getting the king to move down the rows is if we're like here, if we're on some row, and the king is on the row right below us, and we move down, then now the king can move back up, and our plan failed, and now we don't know what to do. So we need to make sure that when we move down, the king cannot be on the row right below us. Otherwise, we will lose. Probably. I mean, unless the king is dumb, but we can assume the king is not dumb. So, how do we ensure that the king is not on the row right below us? Again, let's think about this. So here, if the king is here, they must move down. And whenever we get the input that the king is moved down, we should move down with him. And whenever we get it down, we always move down, unless it's the 7th row. Well, actually, yes, that would work. That makes sense. Whenever the king moves down, we will always move down. And eventually the king can't go down anymore, and we'll be on the 7th row. It'll be perfect. So we just need to force the king to go down. So initially we're here, and we guard this, and so this position is death for the king. So maybe he's like not there. So if we move here, now this position is death. The king is forced to go to one of these squares. And in general, when the king is directly below us, the only way they can go is down. So if the king is on this row, and they stay on this row, as we move along, eventually the king will be directly below us, and so they are forced to go down. So that part's nice. But what if they aren't on this row? Suppose they're like on some other row. So here's like sort of the casework. So same row, forced down. What if it's on, or like, not same row, like right below? What if he's not right below? What if the king just sort of like dodges? Like every time they just move left or they just move right? Well, if that's the case, then they are not forced down. If they never make a vertical move at all, if they don't go up and they don't go down, then they are never forced down, which means they cannot be on this row. So this is a check mark, means we can go down. If they make no vertical move, then they cannot be on this row, because if they were, they would be forced to go down. So because they're not on this row, that means they're on some other row. And because they made no vertical move, they never moved up to this row, meaning that we're safe to go down, because the king can't evade us. So if they make no vertical move as we slide along here, then we're good. Otherwise, they move up somewhere, like they move in one of the 3 directions up. Because if they go at any point down, we move down, we continue our strategy. It's the same thing. So what if they move up? And the problem is, like, we don't know what kind of up they moved. Like, maybe they're here and then they go up to our row, and then it's unsafe to go down. But what if they're like all the way back here and then they move up? And then it's fine to go down, but we can't distinguish that, is the thing. So when they go up, it sort of seems like it ruins the strategy, because they go up a row, we still are unsure of whether we can move or not. But the key idea is that they can't go up forever. They can only go up until they hit right below, and then they're forced down again. So think of it like potential energy, kind of. Like, they can move down a row, but then they, like, when they go back down, we also move down. So essentially, the number of times they go up and we can't move down is limited. It's at most like 6 times that this can happen. And then every other time we'll hit one of these cases. So if one like sweep right takes 7 moves to go right and then 1 move to go back, so it's 8. Then we make 6 moves down. So we make 8, and then maybe we like go down. So let's say 9. And then we do this 6 times until we're on the last row. So 54. And then maybe we waste 8 times. We waste like 8 moves every time this happens. But that can only happen 6 times. So we end up with 48. In total, this is 102, I believe. Yes. So in total, this is 102 moves to get to the last row. And this is like sort of worst case, because if we ever go down, if the king ever goes down, we get to break early. We get to go down too. And we sort of skip this like dance that we do with the king. So as long as we hit one of these cases, and we're guaranteed to eventually, even if this happens a few times, it cannot happen forever. Eventually the king will either be here or they'll move down and then we'll move down. Or like they'll either be on this row and forced down, or they won't move, or they'll move down. So this is like, it's more like only up. So this is 102 moves. Then for the final step, once again, we do the strategy we started with. We just sweep along. So this is maybe like 5 to 6 moves to 108. It doesn't cost that much, is the point. So yeah. So in total, to get the king on the bottom row, we spend at most like 102 moves, or like around that. Not close to 130. And then for the final thing, we just do that. We sweep along, we mate the king. And everything works. Can I see tests? How many queries did it use? Not even that many. Yeah, I'm using fewer than the jury. Nice. Sometimes, not always. But yeah, that's the strategy. From like essentially force the king to go down by moving down and not let him go up. And then we trap him on the last row and we mate him. So if the king goes down, we move down. If they don't make a vertical move, then they're not forced down, so we go down. And if they go up, we can't do anything, but that can only happen at most like 6 times or so. So we are good. That is all the problems. System testing is finished. We get like 20 something. Oh, really? Wow, 20th. How did that happen? Do people fail system tests? What happened in my room? And my friends fail system tests on D. Oh, I guess time limit exceeded could happen. It's not even to click. Did anyone fail in my room? Oh, fail on E. Wow. Runtime error. That and that. So yeah, that guy was above me before. He had more points, and now he drops below. So that's cool. I guess a couple other people did too. Sweet. Okay. That is it. Hope you enjoyed. I hope you weren't here to see me do well, because that was not the point of this video. For Div 2s at least, I'm going to transition more towards just focusing on more of the commentary and things like that, because I think like that's sort of the whole point of doing a screencast. There's no point of recording my contest if I'm just clacking at a keyboard and you just like, you know, you just hear that and suddenly all the ideas appear in my head and it's sort of magical and nothing happens, right? That's what I'm getting at. So I'm going to try and do more in that sense. And also I'm going to be a freak and test my audio all the time. But hopefully it worked. Hopefully everything's good. Yeah, alright. Goodbye.